All right, it's time again. Second part of lecture 4. What I did, I split the video recording now into two because I do believe that the quality of the video is reduced because of the total size of the file. I saw that the previous lecture was not the same quality after uploading. So yeah, let's see if splitting the session into the lecture into two sessions help us. I will now move on to continue with the presentation. We have the acting forces still to cover, about to finalize them, moving on to the limitations of what pipes actually can endure in very few slides here. We talked about the temperature, and once you have and understand the difference in temperature, it's not difficult to get the resulting stress. As said, there are three main categories, however, 4 calculations, and they are presented here. These are the calculations that we do in order to find the delta T, delta temperature, change in temperature from what we call initial conditions until we produce. I'm going to repeat that you guys will not be calculating these things, but rather the previous calculation is more to our standard for this class. Now, the understanding of these things would be definitely what we want you to have after taking this class, so that you are prepared not just to do casing analysis for your future company, but also that you are good at seeing potential failures on the rise should difficult situations and so on. Yeah, I have made this slide showing what we call wellhead growth. I will do this to make the slide less crowded. You saw the well, you saw that it's producing, you know the temperature has gone up, you know the stress in the pipe, and the result is what we see here. All these blue arrows indicate that the stress is going on in the infrastructure, the casings of the pipe and that of the well, and that these are all cemented in the bottom. What's going to happen is that the tension level in the wellhead is reducing as you're heating up the steel. The steel is wanting to extend, and that will take place in a relatively advanced calculation, because you need to know the different temperatures influencing the different casings, and they are not the same because of all the temperature effects. You have the advection, you have different things, so that the temperature is not the same going out in the different annuli, and you will have different resulting stresses going up. As said very early, lecture 1, or maybe it was 2, the conductor the conductor, it is holding everything down. So, and that role of the conductor is extremely important, because when you put on the Christmas tree, it holds down, the conductor holds down, and the Christmas tree will stay in place, so that the flow line, especially subsea, but also there are tolerances for where the flow line outlet on the Christmas tree meets the physical pipe that goes into the Christmas tree. In many fields offshore, you can see that there are flexible hoses going into the wells, because the wells are moving. That is a special design, and yes, it does exist to take up any movements that are in the wells, but still there are limitations for even these wells. Now you have seen what it means, wellhead movement, wellhead growth, and for me, my personal experience that I can share with you, I've seen cases where onshore where the conductor has lost its bond, and the pipes are moving, and that's quite bad. You have a limitation there, of course. Say that it's in a case half a meter, 30 centimeters, something like this. If it goes beyond, you will have to do grouting, cement repair jobs, or even other means could, in extreme cases, mean that you have to stop producing the well and take it off production. Yes, back to an overview. We have now closed the matter of the acting forces. We have now also included the calculations of the basics. We didn't do the density differences, thinking that you guys know how to calculate the difference in pressures and over to the stress. We will now move on to what are the physical limitations and how do you calculate the stress limitations. One side of it, of course, is the acting forces. Once you know those, you need to select your pipe, and the pipe will appear in the software of casing design, for example, stress check and WellCat. They will appear as limitations, and we saw that in the let me see, yeah, we're getting onto a plot like, for example, this, and we'll see the stresses in the well going on like these lines here, and that they are inside our design window. That's basically how this will materialize, and we better understand both these are the stresses that occur from the different load cases, the combination of all the acting forces in our critical situations. Now what we're about to embark on is what limitations do we set for ourselves? Where are the tolerances of the different pipes? And what we do now is to start on what is called collapse theory. Collapse is not just the stress of external pressure, it is actually instability of pipes. What we did in one of the early lectures was to talk about what are the different gentlemen providing us with the different equations and theories that we are using. And I think it was in the 1600s, Mr. column. Let me see. The column theory came from Euler in 1744. So we can think about buckling. Buckling, as in a column, is it stable? And that's again the tin can, soda can, standing on it, and a small impact sideways makes it destabilize and completely flatten. So yes, collapse is a combination of external pressure and the stress in the pipe. We see a curve down here in this slide. All the way to the left, we see that in blue we have the smaller, call it x-axis, and it goes up to the highest strength. Explaining the graph a little bit more, of course, going vertical is the stress that call it the material can endure, and the x-axis is the ratio between the outer diameter and the wall thickness of the tubular that we are considering. We see the x-axis graphically represented up to the right, wall thickness and the outer diameter, the ratio between the outer diameter to the wall thickness, an extremely important figure in not just collapse but other means as well in casing design. We will get back to that. In light blue, the column is tied to material yield, and that only. This part of collapse is not influenced by or it's not buckling. It is not buckling at all. Whereas the green all the way on the other side is very much tied to buckling. It is a strength-based calculation based on yield all the way to the left, whereas it's only tied to stability, more or less, a combination of stress and pressure to the right. And the one in the center is a combination of these two. Collapse is very often thought of as the most difficult and advanced part of casing design. As an academic, I say I don't agree. And I will get back to that later on. Basically, because as we are talking about strength, it's very easy to see when a pipe collapses. Whereas going to burst is not that easy. And the calculations are very often, call it, neglected in a way, because collapse theory takes so much room. Maybe a strange and indelicate way of putting things, but I think you will get the understanding of where I'm getting at with that. Moving on. This slide is maybe a little bit hard to see. The numbers, the tiny numbers on top of each blue column would be the casing weight, as in pound per foot. And we see here the distribution for a specific yield. Yield 75,000 psi. And we see different pipes, and knowing that the casing weight pound per foot is determining the DT ratio, we can understand here a portion of where can we find the different pipes. Meaning, the blue column governed only by the material strength. We see that in the bottom here, and we see there are only a few pipes that sort in this category. We have a 7-inch 38 pound per foot. That is very close to the limit between yield strength collapse and what we call plastic collapse. It would make call it the border between category 1 and 2, light blue, and I don't know what we call that color, pink maybe, pinkish. So that's where this 7-inch 38 pound per foot is residing. 38 pound per foot 7-inch, that is a special pipe. It is very heavy walled, and rarely have I seen that in use. 5-inch 25 pound per foot is also in the same category. I have seen pipes in a specific field in the Norwegian sector, the field called Kristin. They have a 15,000 psi wellhead design, because the shut-in pressure is very close to 15,000 psi. They have that type of tubing, so it will fall into category 1, yield strength collapse. And not sure you guys are ready for it, but yield strength collapse is a very strange and special case. We jump to this slide here. These are different pipe failures, all of them collapse. And this is what you guys, I guess, expect to see in collapse. This is collapsed pipe. This is how we visualize it. When it comes to category 1 yield strength collapse, this is not how pipe collapses. It's yielding, it's not collapsing. And for that to make sense to you right now, I quickly go back to this slide and I duplicate it so we don't get confused. I take away everything here like this, and I show you only this slide here. I even take away this one. We remember this point here, yield strength, and it has a 0.2% permanent deformation. So yield strength collapse, it yields, it doesn't collapse. So we start to deform the pipe, but it doesn't do this. And that pertains to only those very special pipes falling into this category. You will most likely rarely see these pipes in your entire career. Doesn't really occur all that often. I give this importance. Why? Because it's so special, and it is something that you need to understand when you do your analysis. When it's close to collapse or the limit for these particular pipes, what do we do? How do we think? Will it have an enormous effect, or doesn't it really matter all that much? We need to understand these things as engineers as we do the analysis. Yes, as we move on to pipes that fall into the plastic collapse and certainly transition collapse and elastic collapse as per definition, we will see these types of failures and the immediate change and defaulting the well for production, disqualifying it, and it immediately turns into a threat of major accident. So these things are in a complete different category than than the yield strength collapse as discussed. Here is a slide I'm going to show you. I am not sure I like this graph. What it does, it shows you the DT ratio and it shows you the yield strength, and here are the different collapse modes. You can see that for the same DT ratio, increasing the yield strength, how it doesn't overlap. I'm not sure that this makes a lot of sense. Maybe if we say DT ratio 25 and we increase the yield strength, going from 55 to 110 plus, then you move from transition collapse to elastic collapse. To me, not sure it makes sense whatsoever to discuss this slide, but you will get across it in the literature, and I tell you, be a little bit careful with it. Burst. This is how much I will give you on collapse in the first blink. We will revert to it and we will look at how to calculate the different collapse modes. For now, we will go into burst and you will see that yes, it's apparently very simple. At least that is how the industry is doing it in the calculations done in most software for casing design, like stress check. This is the formula that you are going to use. Well, the software is not showing this to you, it just tells you we are doing the Barlow formula. And if you take a slightly deeper dive into things, you will see that the standards that are governing how to calculate the loading tolerance for pipe, the ISO 10400 or API 5C3, you will find that they are saying be extremely careful with this formula. And that's a little bit academic. Often what I do coming to this point, trying to explain why this is dangerous, I have to often use an analogy. What the industry is doing is, in this case for burst, you're driving around in an old Volkswagen Beetle. That's what you're doing. It works. It starts in all temperatures. It works for all functions, and it has what it takes to get from A to B. And the industry is saying, why should we change something that works? And that's definitely That's definitely absolutely true from one perspective. Only the thing is that today we have Tesla electrical and we have whatnot. So um, to give more and better understanding, this formula was developed in 1836 and presented, or at least that's when it was presented in public paper by Barlow, and it's long before the theory was settled on modern material science, understanding what was going on, and some of his deductions, they are not entirely correct. I leave you guys to read that in ISO 10400. What was wrong about Barlow's presumptions and calculations, and the formula is actually theoretically valid only for the opposite of what Barlow was saying, all of which you can read it in the standard. It's been there more or less since 2007. The joint, call it academic part of the oil industry is saying, be careful. Whereas on the other side, the users are saying, but it has been working for us more or less forever. And all of it is true. To put even more understanding to why this formula is is a little bit out of place, it has this factor 0.875, or it relates to 12.5%. You just remove 12.5% of what the burst is giving you. Taking away this one is meaning you have the full burst ratio of the pipe, whereas adding it removes 12.5%. You get that. It's very simple, very mathematically easy to see. Now, adding also the DT ratio in reverse here for you guys, just to point to the fact that the DT ratio is important again, also for burst, not just for collapse. This relates to the tolerance of tubular wall thickness. And here is where the industry sits in their old Volkswagen Beetle. Also from 2007, anyone looking a little bit into what the casing manufacturing industry is saying. They are saying we have full control of the wall thickness. It is easy to produce pipes now with a specific wall thickness. And you can find the material to calculate and see the analysis also in the same standards. But the industry is keeping to the 12.5% deduction because driving in the Volkswagen Beetle, it's actually working. So it's a stupid analogy, but I hope that you get the picture. The wall thickness, actually, what the industry is doing is an absolute minimum is 94%, or 0.6% would be a more accurate number, and you would be covering absolutely all pipe manufacturing that are presented in ISO 10400 from 2007. As a personal, to satisfy my personal curiosity, I checked out how long has the industry been working with this 12.5 factor. I found out that it was already implemented in the 1950s, and pipe manufacturing, trust me on this, has improved quite significantly since 1950. Pipes, and you will find that many places, especially on what we call rupture, and we'll quickly move on to that shortly. and the understanding of burst in a better context, it has improved very, very much over the years. And looking into it, say small failures like at an atomic level, all the way up to small, infinitely small cracks. They're all these things are improved, and the wall thickness, control of the wall thickness, very much improved. So anything that ties into old standards, old ways of doing things, they are less important. And there are and all of it comes from the standards, and all of it is documented. All of it can be proven, and it is proven. Here it is, and again, it all ties into the graph up to the right. What you guys see here is a pipe that is ruptured. Rupturing takes place at the very end of the graph here. All the way at the end of it, that's where the pipe ruptures. There is a specific calculation in ISO 10400, the API 5C3, where you calculate rupture of pipe. Meaning that's very easy, because that's where you see pipe are failing, and it ties into all this, call it good calculations. It's the specific yield, and then you know wall thickness, or you know the parameters of the pipe, and you can calculate rupture quite easily, and you can see it. Science is tied to what you can see, measure, and our senses, right? Whereas the difficult part for burst, and here is where maybe I was not easily making sense to you guys before, yield. Here, burst. We say burst, and we often think about rupture. The pipe is bursting, but it's not bursting as what we are thinking immediate. It is yielding, and it's deformed 0.2%. And how do you measure that? You have to have micrometers, more or less, to know that yes, we have changed a piece of pipe 0.2%. It's not much. It's not much. Yeah. So that's the inherent difficulty with burst. The industry is using this formula, and it says that we are tying it to yield, 0.2% deformation, and it all becomes a little bit difficult, at least for me. I'd say when you're using this formula, very old style figures tied to what is not so very often occurring anymore, wall thickness 12.5%, as said, and a calculation valid for I'd say, just to be quick, 70% of these pipes. It is mathematically correct entirely, more or less, by accident, as it says in the standard. And you're trying to tie that to this point that is not so very visible. That's why I'm saying burst is not as easy and straightforward as collapse, whereas 90 to 95% of the pipes, they are governed by this type of visual failure. I'm probably more clear now than when I started out trying to explain this. Burst, it has this type of failure too. You won't see this very often. It's called wrinkling. And that wrinkling part, we will get back to it, and you'll see why it's not so very often visible or at all something that you will very often come across in your professional career. Here is another type of failure, also not very common, but nevertheless a limitation that we need to adhere to. What it does is a pure pull. So when you have too much weight hanging, let's say that you're running a casing string and you have chosen a wall thickness, the wrong DT ratio. Then in that case, if the casing string is so long that it cannot support its own weight, it will fail in this, according to this picture, this failure mode, tension. It will not. It will have what is called necking and part in this way. We will revert to collapse. I will now show you how to calculate the collapse, different modes. Again, the industry Beetle is using, it's an old style calculation. There are more modern ones. You'll see everything in the standard as per se. These lines between 1 and 2, and there is a staple line here, and 3. So there are 1, and then here half of 2 is 1, and then there is a limitation between half of 2 and 3. So we have 1, 2, 3 lines, and there are calculations for each of these lines. And you'll see that we call them DT ratios. DT ratios. And there are factors F1 through 5 in these calculations. What is a little bit okay about this is that these F's, these empirical constants, they are listed and they are easy to deduct, and that comes on the next slide. We punch in those in addition to yield, material yield, and we get the limitation. We know our DT ratio and we know the limitation, and we have different yielding yield strengths listed here, and we know the equation as per se, and then we have the DT ratio. We know that the equations here will give us the different, call it collapse loads. So at a certain value of the DT, we know that, okay, we are in this side, or we are here, or we are here. So it's basically a straightforward, simple calculation to find which area are we in. We are not calculating the collapse strength as per se, just finding the collapse mode in this way. Here are the different empirical formulas. It is listed here how to do it. F1 through F5. F1 through 3, they are with yield strength. F4 and 5, they are not with yield strength. You can calculate these ones yourselves. And maybe if there's time, I can show you an Excel sheet with the steps, how this is calculated. It's a little bit satisfying to actually be able to do this calculation. The next step, as you know which mode you are in which area of this are we? then you can then you can calculate the collapse pressure for yourself. Now, in this first area, and this is important to know about collapse calculations and theory, yield strength collapse is mathematically deducted, and it is more or less very, very accurate. I can say the same about elastic collapse. It is mathematically deducted and very much correct. I can unfortunately not say the same about plastic and transition collapse, and that comes from the fact that they are empirically derived and they are physically tied to the performance of tubulars produced in the 1960s. That's why the collapse pressures are very often hiding a large portion of hidden safety factors. Let's go back to this slide again. We see that the majority of pipes, at least in the 75,000 yield, they reside in transition and plastic collapse. At least of those pipes that we are using, 1338 68 pound per foot is a very common pipe. Very common. You will see that a lot. 72 pound per foot too. When it comes to conductor pipe, they all go up here with a higher DT value. So very common pipe, and yeah, these things these collapse modes are very common. Yeah, so we have the calculations here, DT ratios all over with the F factors added, and you will get the collapse pressure rating according to this standard industry formula. Now, we have to correct collapse for any stress, actual stress, and that's what we do in both these empirical areas. What is important for you guys to know is that those pipes that fall into the area of elastic collapse, it doesn't depend on yield at all. It's independent of yield, so the collapse rating is not corrected for any actual stress. We see also for yield strength collapse that the yield strength goes straight in, whereas actual stress in plastic and transition has to be corrected. This is what I'm talking about. You find the corrected, call it yield. That's what you do. You take your actual stress, you find an expression for it, and you reduce it. Here is your corrected yield strength because of the acting actual stress. And you add that into your calculations for the plastic and transition collapse. Here is what was made back in the early 60s. We see this, this is the same representation as shown to you guys initially for collapse. Yield strength here all the way to the left. Plastic and transition is really one group, split only because mathematically finding a formula that fits within the group and the performance of pipes in the 1960s had to be split like this. We see the different graphs here, if they are punched all over their area and outside their area of validity according to pipe, how it performed in the 1960s. And of course, I will show you how modern pipe perform compared to how these calculations actually do in later class. We have arrived at 10 o'clock, which means that that this session is over. What I'm showing you here is basically the different steps that I just explained. I will not go through it again. I can do that when we start the class on Monday, because then we do always a quick repetition to get into the mode. I will not repeat this. I've said that thoroughly enough. This is what you find in ISO 10400. It lists why you should be careful with the collapse calculations that I just showed you, and I think I've been quite clear on why you should be careful. Also, so much as here it recommends other calculations that are much more accurate, and actually these calculations, they can also be tied into worn pipes, which is what I think, and many other academics with me, that pipes, they are always worn, more or less, and that's important for how you deduct calculations later on. But that's not how the industry is working, doing casing design. They are using the formulas just shown, and they have other ways of calculating stress after wear. And we'll get into all of that later on. Any questions at the end of this class? Good. See you guys on Monday. Have a nice weekend when the time comes.